All right, ready for this? We're taking a deep dive into something really cool today, the double pendulum.
Yeah, it's one of those things that, looks completely bonkers at first glance.
Totally. It swings around like, I don't know, like it's trying to break dance or something.
But here's the thing, all that crazy movement is actually based on, like, really simple physics.
Right. It's just two pendulums hooked together. How hard can it be? But the way it moves, man, it's wild.
Yeah.
And that's why we're here today, to really dig into this thing.
To unpack why something so simple can create so much chaos.
Exactly. So to start, I guess most people have a pretty good idea what a normal pendulum is,
Yeah.
right? You know, like the thing in a grandfather clock.
Yeah, weight on a string. Just swings back and forth.
Nice and predictable. But the double pendulum, well, that's like its wild child cousin.
Two pendulums linked together. And to really understand what's going on, we need to imagine, like, a perfect double pendulum. Like, no friction at all. Just pure physics at play.
Right, so like no air resistance or anything,
Right.
just gravity doing its thing.
Yeah. Exactly. No friction means no energy loss. So in theory, it would just keep swinging forever.
Okay, so that helps isolate like the core principles.
Yeah, and this is where it gets really interesting. We're talking about what's called deterministic chaos.
Deterministic chaos. Okay, that sounds kind of contradictory. How can something be both determined, like pre-programmed, but also chaotic?
Well, the movement of the double pendulum is completely determined by its initial conditions, like the angle of each pendulum at the start, how fast they're moving initially. That sets everything in motion.
So it's like knowing the setup determines the whole path it's going to take.
Right. But here's the crazy part. Even the tiniest change in those initial conditions, and I mean TIY, like a microscopic nudge,
Oh, man.
it can lead to totally different outcomes, drastically different paths.
Bro, so even if you knew the starting point perfectly, you couldn't predict where it would end up.
Nope. That's the chaotic part of deterministic chaos. Think about trying to balance a broom on your fingertip. Pretty hard, right?
Yeah, I'd probably fail miserably.
Now try balancing a second broom on top of the first one.
Oh, come on, that's impossible.
Exactly. The slightest nudge and the whole thing goes haywire. It's super sensitive.
Wow. So what's actually going on, like, mathematically to make this happen?
So the equations for the double pendulum, they're a bit more complicated than for just a regular pendulum. For one, they're nonlinear.
Okay, and nonlinear means... Sorry, not a physicist here.
Well, basically, a small change in the input doesn't necessarily mean a proportionally small change in the output. It's not a straightforward relationship.
So you can't just, like, move it a little and expect it to swing just a little.
Exactly. It's much more complex than that. And on top of that, the equations are also coupled.
Coupled.
Meaning the movement of each pendulum directly affects the other. They're constantly influencing each other.
So they're not just doing their own thing, they're reacting to each other all the time.
Right. Like imagine two people on a seesaw. Their movements are linked.
Right.
What one person does affects the other.
Oh, yeah, that makes sense. Okay, so that's how it gets so unpredictable. So about that simulation we have, does that factor in all this, like, nonlinear coupled stuff?
Absolutely. And that's why you'll find it basically impossible to make the pendulum follow the same path twice, even if you start from the same spot. Want to try it?
You bet. All right, so I've got the simulation up. Let's pull back both pendulums and release. Oh, wow, look at that. It's going crazy.
Right. Now try to get it to do the same thing again.
Okay, same starting angle, let go, and nope, totally different. It's off on its own adventure now. This is impossible.
Yeah, that's how sensitive it is. And remember, this is in a perfect world, no friction or anything, just pure math and physics.
So in the real world, wouldn't a real double pendulum eventually just, like, slow down and stop because of friction and stuff?
Exactly. Friction acts like a brake, stealing energy from the system. Eventually, those wild swings would get smaller and smaller until it just stops.
Ah, so the chaos would eventually fade away because of real-world stuff.
Yeah. But that doesn't make the underlying physics any less fascinating, right?
So even though friction tames it, the potential for that crazy, unpredictable behavior is still there.
Precisely. Like it's just waiting beneath the surface.
That's pretty wild. You know, it's making me think about other things that seem random, but maybe they're actually governed by this kind of deterministic chaos, too.
Like what?
Well, I don't know, weather patterns, the stock market, even human behavior.
You're onto something there. Actually, a lot of researchers think many things we see in the world that seem totally random might actually be examples of this kind of chaos. It's a whole different way of thinking about things.
Whoa, okay, so we might be surrounded by this hidden order that just looks like randomness to us.
Maybe, and that's what makes this whole thing so amazing to explore.
I've always heard that thing about, like, a butterfly flapping its wings in Brazil can cause a hurricane in Florida? Is that like the butterfly effect in action?
Exactly. It's a super popular way to explain how sensitive these chaotic systems are to their initial conditions. Even a teeny tiny change somewhere can have these huge, unpredictable consequences somewhere else.
So that's why they can't, like, perfectly predict the weather, even with all those fancy computers and stuff.
Yeah, it's basically impossible to make long-term weather predictions with perfect accuracy because of that sensitivity to initial conditions. It just means there are too many variables, too many tiny things that could change the outcome.
Okay, so even though we can't predict these chaotic systems perfectly, at least understanding this idea of deterministic chaos gives us like a new framework for thinking about them, right?
Absolutely. It helps us appreciate that even when the rules are simple, things can get really complicated and unpredictable.
It's like there's this hidden complexity lurking beneath the surface.
Exactly. It encourages us to look for patterns even when things seem random.
So it's not just a matter of throwing up our hands and saying, well, it's all random, anything could happen.
Yeah.
We can still learn something from this chaos, right?
Of course. And those lessons can help us in so many areas, from weather forecasting to understanding the stock market to even building better AI.
So we've been focusing on this idealized double pendulum in the simulation. But earlier you mentioned that a real pendulum, with friction and everything, would eventually stop swinging. Does that, like, change things?
Well, yeah, in the real world, friction is kind of a buzzkill. It slows everything down and eventually makes the pendulum stop.
Because it's losing energy.
Right. But the important thing is that the math, the equations that describe the pendulum's motion, those are still at play. Friction just adds another layer of complexity on top.
So even though the chaos is tamed in a real pendulum because of things like air resistance, the potential for it is still there.
Exactly, like a sleeping dragon or something.
That's a pretty cool way to think about it. Okay, so we've talked about the math, we've played with the simulation, we've thought about what all this means in the real world. What's the big takeaway here?
I think the key takeaway is that even really simple systems, when they're governed by these nonlinear coupled equations, can create incredibly complex and unpredictable results. That's what deterministic chaos is all about.
So it's not just randomness, there's order in there somewhere, but it's so complex that it just looks random to us.
Right. And that's kind of a mind-blowing realization, right? It means we might not be able to predict the exact outcome of these chaotic systems, but we can still understand the principles that are driving them.
Okay, this is giving me a whole new way of looking at the world. So if something as simple as a double pendulum can be so unpredictable, what does that say about our ability to predict even more complex systems, like the entire global economy or the effects of climate change?
That's a huge question. And I think it suggests that our ability to predict the future is always going to be limited, especially when we're dealing with these massive systems that have tons of interconnected parts and feedback loops.
So those things are inherently unpredictable to a certain extent.
It seems that way. But that doesn't mean we should just give up on trying to understand them. It actually makes scientific research and modeling even more important. So embrace the chaos, but don't let it paralyze you. Exactly. The double pendulum shows us that complexity and unpredictability are just fundamental parts of our universe. By acknowledging that, we can start to find new ways to deal with uncertainty, and maybe even find ways to use it to our advantage.
Wow, that's a great point. Okay, we've covered a lot of ground here. But before we wrap up, I got to ask, what happens when we take this idea of deterministic chaos and apply it to, say, the human brain? I mean, that's about as complex as it gets, right?
Oh man, that's a whole other can of worms. We're talking about billions of neurons, trillions of connections, all firing and interacting in ways we're still just beginning to understand.
So are you saying consciousness itself might be an example of deterministic chaos?
It's definitely a possibility. Some neuroscientists believe that our thoughts, our feelings, our decisions, all of that might emerge from the complex interplay of neurons, governed by the same principles of chaos we see in the double pendulum.
So free will might just be an illusion.
Well, that's a big philosophical question, and I don't have the answer to that. But I think it's fascinating to consider that even our own minds might be subject to the same kind of unpredictable yet deterministic forces that we see at play in the physical world.
Mind blown. Seriously, this whole deep dive has been incredible. Thanks so much for walking us through all of this.
It's been my pleasure. And remember, folks, the next time you see something that seems random, don't just write it off. There might just be some beautiful hidden order behind it all, driven by the fascinating power of deterministic chaos.
So we're not saying it's hopeless, right? Like, we shouldn't just throw our hands up and say, well, the world's chaotic, there's nothing we can do.
No, not at all. We might not ever achieve, like, perfect predictions, but
Yeah.
understanding these principles helps us refine our models, make better
So
decisions.
it's about accepting the limits, but still trying to make sense of things.
Exactly. Recognizing that even in chaos, there's this underlying beauty, this
Yeah.
order. It's about, like, embracing the mystery and just keep exploring.
Yeah, it's like that saying, what is it? The more you know, the more you realize you don't know.
Uh-huh. Yeah. Perfect way to put it. The double pendulum, it really shows us that the universe is full of surprises, right? Challenges what we think we know. Keeps us learning.
Totally. Well, this has been a truly wild deep dive. Thanks for, being our guide through the chaotic world of the double pendulum.
Oh, anytime. And hey, remember, next time you see something that seems totally random, maybe don't just dismiss it as pure chance. Could be some amazing deterministic chaos at work.
Yeah, I'll definitely be looking at the world a little differently now.
Uh,
Thanks again for joining us for this deep dive. We'll catch you next time.